All right, welcome back everybody. And we are now at project 6 of our Arduino project book, Light Theremin. This little component, if you've ever heard Star Trek's theme, it was with the theremin, a little bit more advanced than what we have. But regardless, same principle, electronic tones from the frequencies that we provide. So what we're going to do in this project is start off like we normally do, diving directly into our code, and then in the next video we'll take a look at the actual circuitry. So here, as usual, we have our setup and loop. All right, we've seen that quite a few times before. But right off the bat, you can see that we have our variables declared pitch as well as sensor value. And with our pitch, you'll notice a comment, don't declare variables in loops. We've alluded to this principle in earlier videos, but here, what I want to point out is if you look at the code in the book, the actual variable for pitch with the int in front of it is occurring inside the loop, meaning that the variable is being allocated and destroyed each cycle of the loop, and it's also been given a value. Well, there's no need to allocate and destroy the variable inside of a loop when all you really want is just a new value into that variable. So here we're declaring the pitch variable outside of the loop, so we only declare it once throughout our entire program. It makes it more efficient, and when we're dealing with embedded and IoT systems, we want to pay attention to things like this. So that's the reason we have that there. Additionally, we are looking at our sensor value, right? The value that we're ultimately going to set for our input. And here, they don't initialize it in the book. I'm a big fan. You always initialize variables. I don't know why they didn't initialize it. A lot of times, you'll get the advantage of a VM like JVMs for Java. They'll initialize your variables, but when you're dealing with embedded systems, smaller boards, you're not guaranteed that, so always make certain that you initialize your variables. So anyways, enough about that. Let's go ahead and take a look at some of our next variables that we're going to be putting in for the values that we're going to be looking at from our sensors. The first two that we're going to be looking at are the sensor low and the sensor high. And what we're looking at here for these values is when we're reading in from the photoresistor, we're reading in on an analog input, right, A0. Well, we'll show that in a second, but we're reading in from one of the analog inputs, so we know we can only have from 0 to 1023. And you'll notice here that we have the low really set to the maximum and the high set to the minimum. We'll look at why we did this in a moment, but these are the variables that we are ultimately going to store the minimum and maximum that we're going to be able to get from our photoresistor. Next, we have this built-in LED. And you'll notice over on the right in the board, this is the LED that we use to look at to know when we're still initializing the board. And then when it turns off, we know that the board has been initialized and we'll start running the loop at that time. And we'll talk how we get this this timing event in here in just a moment in the setup function. Now, once we have that LED set up, we need to take a look at how we're going to write to the theremin. And we're going to write on our pin 8, right, PWM pin that we're going to write out the frequency value that we want the theremin to pitch at. Right, this is what gives us our sound. And from here, we're just setting up our pins in variables. You'll notice in the book they use A0 in a couple places that are hard-coded. And you know, just as an example in the book, they use A0 in 2 places, which is not so bad, right? So if you wanted to change that to analog input 1, okay, you'd only have to change it twice. I get it. But if you had this 100 times in your code, you'd have to go back through and make certain that all your A0 inputs are converted over to your A1. First off, it's tedious. Second off, it's very error prone. So by putting it into a variable here, it just makes our code much more maintainable over its life cycle. Same thing with the output, right? So we're using pin 8, and so all we need to use the variables for tone output pin and sensor input pin. We just use those variables, and if we do want to change them, we only have to change it in one place. So here we're looking at the number of seconds, and this is actually the number of seconds that we're going to use to keep the LED on, and before we decide that the board is initialized and we turn it off. And you'll notice here it looks a little wackadoo, right? Why 5 times 1000? This really makes 5 seconds, right? There's 1,000 milliseconds in 1 second. Sometimes I've seen, there's a hard-coded value of 1 second that equals 1,000. So you do 5 times the 1 second. There's a lot of different ways you can do it. But here, I just wanted to kind of show where we're really getting number of seconds from. You could just as easily have made this 5,000, right? There's no need, there's nothing required that you do multiplied by 1,000. But I just wanted to kind of break it down a little bit. And then, as you get more comfortable with your coding, you'll decide on how exactly you want to, do something like that. But with that being said, what we're going to do now is go ahead and take a look at our setup function. And the first thing that we're going to do in our setup function is actually turn on that LED. And if you noticed earlier, we used the variable LED built in. It's a const within the Arduino development environment. And so when we use LED pin, we immediately go to that built-in LED on the board, which again, over on the right is still outlined with kind of a magenta square, right? That's kind of up towards the little bit towards the upper right-hand side of the board. And here we do a digital write to that LED, and we turn it on, right? We don't blink this one or anything else. We just turn it on high, and this again lets us know that we are in the process of initializing the board, and this is what we're going to look at next. And so what we do is we say while the running time of the board is less than 5 seconds in our case, right? The 5 times 1000. And the millis function really is just stating how long the board has been plugged in, right? So when you first plug it in, you're at 0, and then it starts to tell you, at millisecond intervals, this is how many milliseconds the board has been running. And as soon as as long as it's less than 5,000 milliseconds or 5 seconds, we're going to keep running through this loop. And as soon as we break out of more than 5 seconds, we'll break out of this loop. So what we're going to do here is we're going to continuously read in from our analog pin, which is our phototransistor. We're going to constantly read that in, and each time we do, what we're going to say is that sensor value that we just read in greater than our sensor high? Well, if you recall, we initialized our sensor high to 0. So we're guaranteed, virtually guaranteed, that the sensor value is going to be greater than a high of 0. And so we're going to set our high value to something more realistic. Next, we're going to look at that sensor value, and we're going to say, is it less than our low? Well, since we set the low to 1023, which is as high as you can possibly get, we know that the current sensor value is going to be less than that low, less than or equal to, right? I mean, it's possible it could come out to 1023 as well, but it's very likely to be less than 1023. And so then we're going to set the low value to something more reasonable. In this first iteration, there's a good probability that both sensor high as well as sensor low are going to be the exact same number. But again, we're cycling through this, a couple thousand times. And so as we go through these values a couple thousand times, we're going to get a more stable, realistic value for high and low. And so we just have an opportunity to play with averages, really. And so that's what we're doing. That's all that we're doing here, is trying to figure out what our high for our photo transistor is going to be and what our low is likely to be. And that's pretty much about it. Once we break out of that 5 seconds, the only thing that we're going to really do is we turn off that built-in LED, right? We turn it to low, right? So there's no more light coming in on it. And as soon as we're done with that, we're breaking out of the setup and we're about to jump into our loop function, right? And so that's why we paid attention to that LED, or you'll see when we walk through the board, we pay attention to that LED. And then when it turns off, we know that the board is good to go, and we're very likely to start getting some sound from that theremin. And talking about that, everything else is going to happen in the loop function. So let's go ahead and jump into that. In the code for this, it's pretty low, pretty small amount of code. The first thing that we're going to do is we're going to read from our phototransistor, right? We're going to get a value, whatever the sensor value may be. And from there, we're going to take that sensor value, we're going to use the map function once again, and we're going to take the sensor value and we're going to figure out where the sensor value falls between the sensor low and the sensor high that we calculated up in our sensor, or in our setup function. And then we're going to map that to an associated value between 50 and 4,000. Now, we've spoken a lot about digital pins taking 0 to 255, and so we'll talk more about where we're getting this 50 to 4,000 from here in a moment. But we're mapping the phototransistor's input to a value between 50 and 4,000. We'll talk more about that, but that gives us our pitch, how loud or quiet it's going to be. From there, we have our tone function. And our tone function is actually what's writing out, we can see here that it's the tone output pin. This is what's actually writing the pitch out to the theremin, which could be up to 4,000. In spite of the fact that we said the pulse width modulated pins can only go up to 255. So we'll talk more about that. And then the 20, that's a hard-coded value. You could change this, but it basically says produce this pitch on the theremin for 20 milliseconds. Once that's done, it's going to delay for 10 milliseconds, and this again just gives the board an opportunity to process out everything and gives a consistency to the theremin to hold that tone for at least 10 milliseconds, right, as opposed to, at 1,000 hertz. So it just says keep this tone on, and then keep it on for 20 milliseconds and then delay 10 more milliseconds before you recycle this whole thing again. That's all that we're doing here. But what I want to do now is really jump into this tone part, since we are writing out to a digital pin, and we could be writing out a value much greater than 255, right? Because we're mapping between 50 and 4,000. So the tone is a function written for us. So it takes that 0 to 255 into account. So when we give that pitch, it's doing some calculations underneath the hood for us to differentiate between frequency and value. So when we're taking a look at this tone, once again, we're going from 50 to 4,000, which means our pitch could be very high, and our tone is taking that into account, and our tone is writing out to our pin 8, and it's writing out this potentially large value. However, what's important here to take into consideration, really, this is kind of the way the book describes it, and you'll find a lot of this text on the internet. But realistically, to take this into perspective, what the 0 to 255 represents is the minimum and maximum value that a digital pin can handle. So, right, it could go up to 255 or all the way down to 0. And what we're talking about with pitch, which is really our frequency, it's how often that value can be pushed into that pin. So let's say that the value, for the sake of argument, is 128. Okay, that's well within 0 to 255, no problem. But if I send that frequency, if I send that value of 128 to the pin 4,000 times a second, that's okay. I haven't extended past the value of 255. I've just given it a value that it can easily handle, 128. and I've given it to it 4,000 times, right? And so really to kind of clarify some of this, it's 0 to 255 is the minimum and maximum value. How frequently you give that value to the pin really kind of depends on what hertz the chips run on the given board, right? So 4,000 hertz, even if I give it the value of 255, which the pin can handle, I'm just going to give it 255 4,000 times a second, right? And so that's really a kind of easier way of looking at it, and it gives you the idea between value, what they're calling duty cycles, and you get into the square waves and everything else. But that's what it is, right? You got a value and then you got a frequency, and so that's why we get the 50 to 4,000 going to a pin that can handle from 0 to 255. All right, so with that being said, in our next video, we're going to go ahead and walk through the board, which is pretty straightforward and can produce some pretty interesting sounds. So we'll see you in the next video. Take care, everybody.